Hello everyone, this is Sir Aris. Let us talk about line integrals. Um, let's uh, start our discussion with recalling our definition for work. The work done by a force F on an object which undergoes an infinitesimal vector displacement dr can be written as uh, F dot dr. So our work done is denoted as dw here. And suppose the object moves along some path with a force F acting on it, varying as it moves. That is, F is a function of x, y, z. So if this is a plot for our x, y, z coordinate system, and suppose this is some point A and some point B, and an object moves along this path. Generally, this force F would depend on the position. So for example, if the object is right here, this is the direction of dr. F could be, for example, F. If it reaches this point, F could change uh, either in direction or in magnitude. So suppose F becomes like this is our dr, so it changes, it depends on the position x, y, z. On a curve, so this curve here, x, y, z are related by the equations of the curve. So there will be only one independent variable, and we can then write f and dr, which is given by generally by this expression, as functions of a single variable. The integral of dw, which is the integral of f dr, becomes an ordinary integral of a function of one variable. This integral is called a line integral. For example, given the force F equals x, y, I minus y squared j, find the work done by F along the path. So there are four different paths indicated in the figure. So the object starts from 0, 0 to 1. First is a straight line. So this is a straight line, passes through 0, 0 and 2, 1. So the slope would be 1/2. Y intercept is 0, so the equation of the line is y equals 1/2 x. So for this part, the second one is a parabola. So this path number 2 here, that's a parabola. Uh, the vertex is at 0, 0. It passes through 2, 1. So our equation for the parabola would be y equals some number to the power of times x to the power of 2. So if x is 1, or if x is 2, then y should be 1. So this should be 1/4. Okay. And the third path is when so first path is a straight line, second path is a parabola. Third path, you go up vertically and then horizontally to the right. So you split, you use two paths, straight line paths, horizontal and vertical, then you add them. So first is this line x equals 0 and this line y equals 1. And lastly, we have a path described by these parametric equations: x equals 2t cubed and y t squared. So that's our path number 4 here. Solution. So since r is generally xi plus yj plus zk, then dr is dxi plus dyj plus dzk. So f dot dr equals f is xy minus xyi minus y squared j. So the x component is xy times dx minus y squared dy. Okay, so we want to evaluate w, which is the integral of f dot dr, or the integral of xy dx minus y squared dy. But take note, we still have two variables here. We mentioned earlier that in a curve, there's only one variable. So that one variable would depend on the path we choose. For example, along or the relation with this to that one variable. So along path 1, for example, you have a straight line with equation y equals 1/2 x. Okay, so that's this one, y equals 1/2 x. So given this expression, then we have dy equals 1/2 dx. Now we can substitute all the y's and dy's here by this two. So we have w equals integral of x, y is 1/2 x, dx minus y is again 1/2 x squared, dy is 1/2 dx. Now the limits of integration, because we're only considering the x-axis here, then this would be from 0 to 2. Okay, from 0 to 2. So this is from 0 to 2. Let's simplify. You have 1/2 x squared minus 1, this is 1/4, so 1/8 x squared dx from 0 to, you can further simplify this, 1/2 x squared minus 1/8, 1/2, that would be 4/8 minus 1/8, that's 3/8 x squared dx. X squared, take the integral, that's x cubed over 3, so this would be x cubed over 8, evaluated from 0 to 2. So x cubed, substitute 2 with x with 2 here, so this would be 1 minus 0, or simply 1. Okay, so the value for w is 1. So here we have substituted y with 1/2 x. How about if we, so just as a check, we should get the same result if we substitute x for y. So substitute, so if we substitute x for y, that is, so some expression for x on y, then we have x equals 2y and take the derivative, dx equals to dy. So our w, which is xy dx minus y squared dy, that would become, x becomes 2y times y, dx here becomes 2 dy minus y squared dy, evaluated from our limits of integration b, so along the y-axis 0 to 1. Okay, so this is from 0 to 1. Okay, 2y squared times 2, that's 4y squared minus y squared, that would be y 3y squared dy from 0 to 1. Take the integral, this would be y cubed, evaluated from 0 to 1. The answer is 1. The same with the one we found here. So no matter if we substitute y with some expression of x or substitute x with some expression of y, we get the same result. For a different path, let's choose along path number 2. Along path 2, we have a parabola um, with equation y equals 1 over 4 x squared, so that derivative of y is 1 half x dx. So 2 goes down here, 2 divided by 4, that's 1 half x dx. So w, which is xy dx minus y squared dy, if you substitute y with some expression of x, you have x 1/4 x squared dx minus 1/4 x squared squared, that's our y squared here, dy is 1 half x dx. Okay, and since we're using x variable here, then it goes from 0 to 2. Okay, so you have 1 over 4 x cubed minus here it's 1 over 16 times 1 half, that's 1 over 32 x 4 times x, that's x 5. Okay, and if you evaluate this, then you have x to the power of 4 divided by 4 times 4, that's 16, minus x to the power of 6 divided by 30 times 6, so 32 times 6, that's 192. All of this evaluated from 0 to 2. So if you substitute this 2 here, x with 2, you have 2 to the power of 4, that's 16, so that's 1. With 0, that's 0, so 1 minus here x to the power of 6, or 2 to the power of 6, it would be 64. 64 192 divided by 64, that's exactly 3. So you have here 1 over 3. Okay, which is in our case, or here would be 3 over 3 minus 1 over 3, that's 2 over 3. And take note here that for the first path, the answer is 1. For the second, the answer is 2/3, different from that path. Now along path number 3, okay, so it's a broken line. Suppose this is your x-axis, this is your y-axis, 0, 0. You have here our point 2, 1. Start here, we go up along the line x equals 0, and then from here we go to the right along y equals 1. So from 0, 0 to 0, 1, so this point, you have x equals 0. So w, which is xy dx minus y squared dy, becomes, so x equals 0. It would simplify to just this, so negative y squared dy integrated from 0 to 1. Okay, so y squared dy, that's y cubed divided by 3. So this is negative 1 over 3. From 0, 1 to 2, 1, the equation is y equals 1. So y equals 1, that's a constant. So here y equals 1, but dy is the derivative. So from here, y equals 1, dy equals 0 because it's a constant. So we're left with this. W equals integral of x dx, where we run from 1 or 0 to 2. Okay, so we get just adding the two results, the two paths. You have w equals negative 1/3 plus 2. So negative 1/3 plus 2. So this would be 6 over 3. So that's 5 over 3. And again, this 5 over 3 is different from 2 over 3, different from 1. Now along path number 4, you have parametric equations 2t to the power of 3 and y equals t squared. Okay, that's our equations here. 2t cubed y equals t squared. So in this case, dx is 6t squared dt, and dy is 2t dt. We're just taking derivatives. Now at the origin, the value of t, so if this is 0, this is also 0, t should also be 0. At 2, 1, what should be the value of t? Find the value of t such that when x equals 2, you have this expression. If y equals 1, you have this expression. So when y equals 1, t is 1. When x equals 2, t is also 1. So we have t equals 1. So our work, so xy dy dx minus y squared dy. So you get here integral of x is 2t cubed, y is t squared, y squared is t squared squared, dy is 2t dt, evaluated from 0 to 1. Okay, so we have 2t cubed, that's 2. What else here? I think dt, this here is supposedly should have t6 t squared. Okay, so here this is 6t squared dt. So you have 6 times 2, that's 12, t to the power of 7. Okay, minus, so this is t squared squared, that's t to the power 4 times t, that's t to the 5 times 2. Okay, the limit is from 0 to 1. So this would give us, let's evaluate the integrals first. You have 12t, so that's 12t8 divided by 8 minus 2t6 divided by 6 from 0 to 1. So you just substitute this by 1. So 12 divided by 8, that would be 12, that would be 3 divided by 2 minus, so 2 divided by 6, that's 1 over 3 This can be further simplified. 2, so 2 times 3, that's 6. 3 times 3, that's 9. 2 times 1 is 2, that's 7 over 6. Okay, so here, path 4, we have 7 over 6. Path 3, we have 5 over 3. Path 2, path 1, you have 1. Um, path 2, you have 2 over 3. Okay, so all different. For let's consider conservative fields. A force field for which W depends upon the path as well as the endpoint is called non-conservative. So for this example, the value of W depends on the path. So path 4, 7 over 6, path 3 is 5 over 3, and so on. So this means that the energy has been dissipated, for example, by friction. For conservative fields, these are those which f dot dr is the same between two given points regardless of what path we calculated along. Um, so in this case, you can think that there's no dissipation of energy. So the work done is independent on the path we choose. In a later section, we will be able to see that del cross f is a necessary and sufficient condition for integral of f dot dr to be independent of the path. So it means that if del cross f equals 0, or del cross f equals 0 for conservative fields, and del cross f not equal to 0 for non-conservative fields. So we can easily see why this is so. Suppose that for a given f, there is a function w such that f equals delta w equals this. So I partial w with respect to x plus j partial w with respect to y plus k partial w with respect to z. So here we can write down the components. So fx is partial w with respect to x, fy is partial w with respect to y, and fz is partial w with respect to z. Now let's assume that the partial derivatives commute. So for example, partial w with respect to x, or partial square w with respect to x with respect to y. So that's equal to second partial derivative of w with respect to y and with respect to x. So if we switch the positions or the order of derivatives, we assume that it doesn't change. So you have this assumption. It means that if you take the partial derivative of fx with respect to y, you have this with respect to y. You can interchange, so you can take the partial derivative with respect to x of fy, this one. Okay, or let me write that again. So partial of fx with respect to y, that's equivalent to partial with respect to y of fx, which is partial w with respect to x. Okay, this is partial square w with respect to y with respect to x, but we can interchange the two. Partial x, partial y is partial y or partial respect to x of partial w with respect to y, which is this. So you have partial f y respect to x. Partial fx with respect to y equals partial fy respect to x. Similarly, um, we get partial f of, for example, y with respect to z is equal to partial derivative of f z with respect to y. You can do the same process just like this. Also, if you have partial f with respect to x, or partial fx with respect to z, that would be equal to partial f z with respect to x. Now, if we use our definition for curl of f is given by this. So that's when we evaluate this determinant. If partial fz respect to y is here equal to partial fy respect to z, then this is 0. This will also be 0 because of this, and this is 0 because of this. So the three components are equal to 0. Thus, if f is equal to del w, then the curl of f is equal to 0. So if we can write f as a um, gradient of some w, then the curl of f is 0. Conversely, it can be shown that if the curl of f is 0, then we can find w, for which f equals delta or del w. Um, if f equals del w, we can write f dot dr like this. We have this dw. So if you integrate f dot dr, that would be the integral of dw, which is just w. So if we integrate from a to b, so we evaluate this from a to b, or simply w at point b minus the w at point a. So WBW mean the values of the function w at endpoints a and b of the path. So regardless of the path, it only depends on the values at the endpoints. It's independent on the path. If f is written like this, so this means that if f is conservative, since the value of the integral depends only on the endpoints, it is independent of the path along which you integrate from a to b. That is, f is conservative. The differential dw is called an exact differential. Um, so del cross or the curl of f, if it's 0, is a necessary and sufficient condition for f that dr to be an exact differential. Generally, for any vector f, if del cross f is 0, there's a function phi called the scalar potential of f, such that f equals negative del phi. In mechanics, if f equals del w, then w is the work done by f. So we can also relate f or w with the potential negative phi. Examples show that this is conservative and find a scalar potential phi such that f equals negative um, del phi. So our first step is to take the curl del cross f equals I jk partial respect to x, partial respect to y, partial respect to z, and the x component 2xy minus z cubed, y component x squared, z component negative 3xz minus 1, take the determinant. So for ith component, for example, it's partial derivative of y, partial derivative of this with respect to y, that's 0. Partial derivative of this with respect to z, that's also 0. For kth component, partial derivative of x with respect to x squared, that's 2x. Partial derivative of this with respect to y, that's also 2x. So they would cancel. And for jth component, partial derivative of this with respect to x, that's 3z squared, negative 3z squared. And partial derivative of this with respect to z, that would be also negative 3z squared. So they would also cancel, which means that this is 0. And therefore, f is conservative. So for w, from some position endpoints a, b, f dot dr, that would be equal to So the this is the x component to xy minus z cube dx plus x squared dy minus 3x z squared minus 1 dz. Okay, so to evaluate this, we need to um, choose a path to go from A to B, but we did not really specify what this A and B are. So let us um, choose A to be the origin. Okay, so this is just a specific choice because for convenience, so that the values are 0, 0, 0. So we also right here we also choose a convenient path of integration. So we have started with 0, 0, 0 for convenience, and suppose we are aiming for um, so we arbitrarily choose um, from A, which is at the origin, to B, which is at x, y, z. So it could be any point. Okay, and A could be any point also, but for convenience, we chose the origin. So we choose 0, 0, 0, 0, 0, and then instead of going straight to x, y, z, we go to x, 0, 0 first. Okay, so that we can easily set the values for y, and then x, y, 0, and then x, y, z. So from 0, 0, 0 going to x, 0, 0, you have y and z both 0, so dy, dz are 0. Also, so x would be just x. So for our w, dy and dz are 0, y and z are 0. Everything have yz. So here dy 0, this is 0, yz 0, so w is 0. How about x 0, 0 to x, y 0? Okay, so in this case, we go from x 0, 0 to x, y 0. What will matter the value of x here? We have x a constant, did not change, so dx equals 0. Also, z equals 0, so dz equals 0. So we go here, dz is 0, dx is 0, x is constant, so w equals integral of x squared dy. Y goes from 0 to y, so 0 to y. X squared is a constant, so the integral of dy is y from 0 to y, so this is x squared y. Finally, from x, y, 0, we go to x, y, z. In this case, x is constant, um, y is constant, so dx equals 0, dy equals 0. Okay, so dx equals 0, dy equals 0. Um, z or x and y are constants, so x is constant here. You have z. Um, a variable. So you have w would be equal to the integration limits 0 to z. Let's put the negative here. You have 3x z squared plus 1 dz. X is a constant. Okay, 3x z squared plus 1. So this would be negative, take, so the integral of this, so that would be x z cube plus z. Okay, so adding the 3, you have w equals 0 plus x squared y plus negative x z cubed plus z. This finally gives us phi equals negative of this. So you have negative x squared y plus, so negative of this x z cubed plus z.